Good morning everyone. My name is G. Vishnumurthy. Lecturer in Physics, Government Degree College for Women, Vanaparthi. Today my topic is Network Theorems. It is covered in 8th paper, first unit, that is Network Theorems. In Network Theorems, we will discuss about Norton Theorem, Thevenin Theorem, Maximum Power Transform Theorem. Here we go for Norton's Theorem. For the reference books are Introductory Circuit Analysis, written by Robert L. So and so. These are the reference books. You may see these books for the network theorems. And here is the network theorem. The statement: any linear active bilateral DC network having a number of voltage sources and or current sources with resistance can be replaced by a simple equivalent circuit having single current source, that is IN, and for Nortons, I for current IN in parallel with a single resistance Rn, where Rn is called as the Norton's resistance. So this is the statement about the Norton's theorem, where IN is known as Norton's equivalent current through the terminal AB, and Rn is the Norton's equivalent resistance waved back into the network from terminal AB. Note: independent voltage sources are short circuited and independent current sources are open circuited. Dependent sources will remain in the circuit for the calculation for Norton's equivalent resistance. So this is about the Norton's theorem and statement, the terminology of Norton's theorem. Very simple. We can understand by using the Norton's theorem. We will simplify the complex network into simple network, or converting the complex network into simple network. That is, all resistances are replaced with only single resistance, and current sources are replaced with only single current source. This current source is parallel with the single resistance. Then the network is called as the Norton's network. Here you see the Norton's theorem, procedure of converting by circuit into Norton equivalent circuit and calculate the Norton's current. So here is the step are there to calculate the Norton current. So before we going to simplify the network, we will calculate the network current, that is the Norton current. So step 1 is remove the load resistance RL and through which current is required, and short circuit it. Let terminal of load are labeled as AB, therefore AB is the short circuited. So the first step in Norton theorem is to remove the low resistance across the terminal AB, and therefore AB is the short circuited. And step 2, find the current through the terminal AB by applying KCL or KVL, Ohm's law, or superposition principle. So this current is the short circuit current, and it is known as the Norton equivalent current, that is IN. So after we will calculate the IN, then we calculate the Norton's resistance, R equal to the Thevenin resistance. So step 3 is set all independent voltage sources as short circuit and current sources open circuit. So dependent sources will not be changed. So in the first 1 and 2 steps, so we will remove the low resistance, and AB is the short circuited. But here we calculate the resistance of Thevenin circuit or Norton circuit. So set all independent voltage sources as short circuited and current sources will be open circuited. Then step 4, to calculate the resistance as seen through the terminal AB into the network. So this resistance is known as Norton's equivalent resistance or Thevenin equivalent resistance. So then after we will calculate the resistance as seen through the terminal AB into the network. So this resistance is known as the Thevenin resistance or Norton resistance. Now draw equivalent circuit. So replace the entire network by Norton equivalent current IN is parallel with the Norton's equivalent resistance Rn, and current and connect the lower resistance RL across the terminal. So these are the main important points, steps in accordance of network, that is Norton's theorem. So before, first we will calculate the Norton current, and then we will calculate the Norton resistance. The Norton current is connected with parallel with the Norton resistance, and lower resistance will be connected across the terminal. So that final network is called as the Norton network or simplified network. Here you see this Norton's theorem is applying in this circuit. So here the linear active bilateral network, this is called as the bilateral network, and this is called as the Norton equivalent network. So this equivalent network is equal to the Norton's network. So here you see this IN is called as the Norton's current, and RN is called as the Norton resistance. This Norton resistance is connecting to Norton's current with parallel, and also lower resistance across the AB terminal is also connected parallel to the IN to RN. So this is called as the equivalent circuit for the bilateral network of Norton's theorem. And then other example is here is, so find the current through 3 ohms resistor by Norton theorem for the network as shown in the figure. Here you see this, this is the voltage source, and another voltage source is there. So this is 24 voltage source, and it is 12 volts voltage source, and it is the 6 ohms resistance, and it is denoted with R1, and R2 has 1 ohms, and R3 has 3 ohms. So this is the complex network, because of in this network we have 2 voltage sources and as well as 3 resistance sources are there. So that's why this network is called as the complex network. So then we will converting this complex network into network, Norton's network. So these 3 resistances are replaced with only 1 resistance, that is called as the Norton resistance, and the 2 voltage sources are replaced with only current source, so that is called as the Norton current source. So how we will convert this complex network into network into Norton's network. So here is the step 1 to calculate the RN, that is Norton resistance. So calculate the calculation is same as Thevenin resistance. So redraw the current circuit by removing the 3 ohms. That is, here is the 3 ohms is removing resistor, and short circuited the voltage sources as shown in the figure 1b. Here is here you see this. So from this we will calculate the Thevenin resistance or Norton's resistance. So therefore the Norton resistance principle is R1 R2 by R1 plus R2. So therefore here we will remove the 3 ohms resistance. So that's why. So 6 ohms is series with the 1 ohm. That's why that total resistance according to the Ohm's law. So therefore Rn is equals to R1 R2 by R1 plus R2. So therefore R into 1 by R plus 1 is equals to 6 by 7 is equal to 0.857 ohms. Okay, so these three resistances are replaced with only single resistance, that is called as the Thevenin resistance or Norton's resistance, that is equal to 0.857 ohms. And step 2 we will calculate of Norton's current IN. So that's why the short circuit the terminal AB and the current flow through the AB is called as the IN. So here you see this the current flow. Here we will short circuited the complex circuit. Here we will remove the 3 ohms resistance between the AB terminal, and those are connecting to each other. That's why the circuit will be short circuited. So therefore the current is passed through the resistance R1 is called as the I1, and the current is flowing through R2 is called as I2. So here is I1 is accordance of 24 volts, and I2 is accordance of 12 volts. So therefore the total current IN is equals to I1 plus I2. So here it is, we know that R1 is equals to 6 ohms and R2 is equals to 1 ohm, and V1 is equals to 24 volts and V2 is equals to 12 volts. Here we will calculate the I1 individually and I2 individually. So according to Ohm's law, I is equals to R by V, sorry, V by R, that's why. So V by R, V is equals to 24 divided by R is equals to 6 ohms. So therefore 24 by 6 is equal to I1. Next I2 is equals to V2 by R2. So V2 is equals to 12 volts divided by 1 ohm. It is equals to 1 ohm. So therefore 24 by 6 plus 12 by 1 is equals to 16 amps. So in this calculation we will find out that Norton's resistance, that is equal to 0.857 ohms, and Norton's current, that is equals to 16 amperes. So the linear network is that is the Norton network is appeared as only single resistance, that is equal to 0.857 ohms, and the current IN is equals to 16 amp. So the network Rn is equal to 0.875 and IN is equals to 16 ohms and RL is same. So then after we will substituting IN and Rn, then we will calculate the lower resistance across the terminal AB. So RL is equal to, we know that R by Rn plus RL. So from that equation we will calculate the lower resistance across the AB terminal. So this is about the Norton's theorem. And now we are going to Thevenin resistance. For the Thevenin resistance, the reference books are there. So from these reference books, you will see and rewrite the notes from these books. So here are the some authors and here are the some book names. So Thevenin theorem. So statement: in any linear active bilateral AC network, the load across its terminal AB can be replaced by a simple equivalent circuit having a single AC voltage source, that is VTH, in series with a single impedance, that is ZTH. So it is called as the Thevenin theorem. From Norton's theorem, we will replace the all resistance with only single resistance, that is Norton's resistance, and voltage sources are replaced with single voltage source, that is current source, that is equals to IN. But in the Norton's theorem, the Rn is parallel to IN. But here in Thevenin theorem, the resistance, the R impedance is connecting the parallel with the Thevenin voltage. So here where VTH is known as the Thevenin equivalent voltage across the terminal AB, and ZTH is the Thevenin equivalent impedance waved back into the network from terminal AB. So note, independent voltage sources are short circuited and impedant current sources are open circuited. So dependent source will be remains in the circuit for the calculation of Norton's equivalent resistance. So this is about network theorem statement, and steps are involved in Thevenin theorem. So procedure for converting any circuit into Thevenin equivalent circuit and its calculations. Step 1. Identify and temporarily remove the impedance, that is load impedance ZL, through which the current is required. Suppose these terminals are labeled as AB, therefore AB is the open circuit. That is step 1. And step 2, find the voltage across the terminal AB by applying KCL or KVL, Ohm's law, or superposition principle. So this voltage is the open circuit voltage VOC, and it is known as Thevenin equivalent voltage, that is represented with VTH. And step 3, set all voltage sources short circuited and current sources will be open circuited. Step 4, calculate the impedance as seen through the terminals AB into the network. So this impedance is known as the Thevenin equivalent impedance, that is denoted with ZTH. And step 5 is replace the entire network by Thevenin equivalent voltage VTH in series with the Thevenin equivalent impedance, that is ZTH. And step 6, reconnect the previously removed impedance, that those are load impedance ZL, to this circuit. So these are the 6 steps involved in the Thevenin theorem. So first step is identify and temporarily remove the impedance through which the current is required. Suppose these terminals are labeled as AB, therefore AB is the open circuited. Step 2, find out the voltage, that voltage is known as the VTH. And step 3 is set all voltage sources short circuited and current sources will be open circuited. Step 4, calculate the impedance, that is called as the ZTH, and replace the entire network by Thevenin equivalent voltage as well as Thevenin equivalent impedance ZTH. And again we will reconnect the removing load resistance across the AB terminal and then find out the Thevenin's current. So these 6 steps are involving in the Thevenin theorem. And then for example we will take as the, and this is the bilateral network and it is converting into Thevenin equivalent network. So these diagrams 1A and 1B showing the Thevenin theorem in AC networks. So another example is there, find the Thevenin's equivalent current of the network viewed from terminal AB. From this terminal AB we will calculate the Thevenin's equivalent circuit. So how it is possible, let's see. So first we are going to remove the load resistance across the AB terminal. So that's why the 2 ohms resistance will be removed. Then we will weaving from AB terminal, then find out the Thevenin resistance. So that is remove 2 ohms resistor, set the voltage source to 0, that is short circuited, and redraw the circuit as shown in the 2B. So therefore the calculator of ZTH, that is called as the Thevenin voltage. For the Thevenin voltage we will call as Z1 is equal to JXL is equal to J8 ohms, that is here is the 8 ohms, and Z2 is equals to minus 6 ohms. Because of these are opposite directions are there, that's why the Z1 and Z2 are in parallel. So that's why we will calculate the ZTH is equals to Z1 Z2 by Z1 plus Z2. So therefore we will calculating as ZTH is equals to 24 less than or minus 90 degrees. So after we will calculate the Thevenin resistance, then step 3 is involving in the Thevenin equivalent voltage VTH. So that is also find out from, we will applying the KVL. So apply KVL in mesh 1. So here is we will apply KVL, then we will calculate the I is equals to here the 5 less than minus 90 degrees amperes, and also VTH is equals to 30 less than minus 180 volts. So this is about Thevenin's theorem and Thevenin AC network. Finally we will draw the Thevenin network for removing all these ohms resistances will be removed and connecting only one resistance, that is equal to ZTH, and also voltage sources is VTH, that is Thevenin voltage is also connecting. Again we will reconnect the load resistance, that is equals to 2 ohms resistance. So 2 ohms resistance is connecting across the AB and that is called as the load resistance. So this network is called as the Thevenin network for the complex network. So this is about the Thevenin network, Thevenin theorem. And third one is maximum power transfer theorem for DC networks. Statement: maximum power transfer theorem states that in a DC network maximum power is transferred to the load when the load resistance is equal to the Thevenin equivalent resistance of the network. Here you see this, the Thevenin resistance must be equal to the load resistance, then the maximum power will be transferred through the network. So this statement is known as the maximum power transfer theorem in the DC network. So we will go to proof. So here we will take as a complex network theorem, Thevenin network here in we are showing. Here VTH is called as the Thevenin voltage, RTH is called as the Thevenin resistance, and IL is called as the load current across the load resistance, and RL is called as the load resistance across the AB terminals. So this network is called as the Thevenin network, because of here we will take as the RTH is series with the VTH. So VTH is called as the Thevenin voltage, RTH is called as the Thevenin resistance, RL is called as the load resistance, IL is called as the current through load resistance RL. So now we will find out power delivered to the load is determined as a function of the load resistance RL. We know that P is equals to V square by R. According to current theorems, the power is indicated with the P, and P is equals to the ratio between the voltage to resistance square of the voltage to resistance. So therefore the power P load is equals to V square load divided by load resistance. So also we know that VL is equals to VTH into RL by RTH plus RL from the Thevenin theorem. So from the Thevenin theorem we will calculating the load voltage across the load resistance. VL is equals to Thevenin resistance multiply with the Thevenin resistance. So therefore the Thevenin resistance is equals to RL by RTH plus RL. Then we will substitute VL into this equation. Then PL is equals to RL into VTH VTH by RTH plus RL whole square by RL. So therefore we got this equation, that is VTH whole square RL by RTH plus RL whole square. So here is RL will receive the maximum power. So therefore we will differentiate equation number 1 with respect to load resistance. So therefore d by dRL of PL is equals to 0. So here we substituting PL is equals to 0. Then we will differentiating this right side equation. So that's why, so d by dRL of PL is equals to this equation. So d by dRL of PL is equals to 0. Then we got the equation RTH is equals to RL. Since theorem is verified. So that when RTH is equals to RL, the maximum power will be transferred. That is equals to P is equals to V square by RL. So this is called maximum power transfer theorem in DC networks. And the maximum power transfer theorem for DC network also, here is another way is, but PL maximum is equal to V square THRL by RTH plus RL whole square. And now PL maximum is equal to V square TH RTH by RTH plus RTH whole square. And PL maximum is equal to V square TH by 4 RTH. Then we will calculate this equation. We got this equation number 3. So power consumed by RTH, that is PTH is equals to I square L RTH. So therefore I square RL. So but IL is equals to VTH by RTH plus RL. Then we will substitute that equation. Therefore PTH, that is power, Thevenin power, PTH is equals to VTH by RTH plus RL whole square into RL. Put RL is equal to RTH, then PTH is equals to V square TH by RTH. So total power supply by the network is equals to PL plus PTH. So PT total is equals to V square TH by 4 RTH plus V square TH by 4 RTH. That is equals to V square TH by 2 RTH, and it is also denoted with the V square by 2 RL. So the efficiency is defined as the ratio of power delivered to the load, that is PL, to the total power supply by the network. And also here we will calculate the percentages, that is neta is equals to PL maximum by P total into 100%. Then we will substitute as PL as well as P total. We got neta is equals to 50%. That is the maximum power transfer theorem is useful in electronic system where maximum power transfer is important than efficiency. In power system, the efficiency is important, so maximum power transfer theorem is limited in power system because 50% efficiency cannot be tolerated. So that is about the maximum power transfer theorem. Another theorem we will already discussing this theorem, so that is Thevenin theorem. Another example is there. Find the value of the load resistance for a maximum power transform. Also calculated the value of the power. So from this network we will calculate the maximum power transfer. Step 1, to calculate the VTH. That's why we will remove the load resistance across the AB terminal and then find out the VTH. So the steps are involved in these steps. When KVL is applied in LHS, then I is equals to 2 ohms, and apply KVL in right side, then we will got as I is equals to 2 amps. So therefore VTH is equals to minus 3 ohms. Then calculate RTH is equal to, by this equation, RTH is equals to 2 into 4, that is 2 ohms is parallel with the 4 ohms. That's why 2 into 4 by 2 plus 4 plus series with the 3 ohms is equals to 4.233 ohms. So this is called as the Thevenin resistance. And then we will calculate, we will substitute RTH as well as VTH in the equation. So we got this type of network. So this network is called as the Thevenin equivalent circuit. In Thevenin equivalent circuit, VTH is equal to 3 ohms and RTH is equal to 4.33 ohms. Next, step 4 is find out the maximum power transfer, that is RTH is equals to RL is equals to 4.33. So calculation of maximum power transfer, that is equal to PL is equals to V square by RTH. Then we will substitute, we got as 0.52 watts. So this is the P load maximum is equal to 0.52 watts. So thank you very much. So these are called as the 3 important theorems are in network systems, network circuits. Those are called as the Thevenin circuit, Thevenin theorem, Norton's theorem, and maximum power transfer theorem.
Hey friends, welcome to the YouTube channel all about electronics, and in this video we will see what is Thevenin's theorem in the electrical circuit. So in the earlier videos of the network analysis, we had seen the different techniques like source transformation, Kirchhoff's voltage law, Kirchhoff's current law, and star to delta and the delta to star conversion. And we had seen that using this technique how we can reduce the network and find the voltage or current across any element in the circuit. Now sometimes it may happen that your entire focus is across a particular element in the circuit and you want to find a voltage or current across this element. So let us say you have this circuit, and in this circuit you want to find a voltage and current through this resistor R3. Now you will say that it is very easy to find a voltage and current through this resistor R3 using a Kirchhoff's voltage law and Kirchhoff's current law. Well, you are absolutely right. You can find a voltage and current using these two techniques. But what if I say that you need to find the voltage and current across this two terminal AB for this 20 different values of this resistor R3? Because sometimes in the electrical circuit you need to see the behavior of the circuit for a different kind of loads. So if I say that you need to find a voltage or current across these two terminal AB for different 20 values for this resistor R3, then if you apply this Kirchhoff's voltage law or Kirchhoff's current law, then it will take a lot of time. So in such cases, Thevenin's theorem is quite useful technique. So using this Thevenin's technique, you can replace the entire circuit across these two terminal AB by an equivalent voltage source in series with a equivalent resistance. So let us see this Thevenin's theorem. So using this Thevenin's theorem, any linear bilateral network containing voltage or current sources can be replaced by a equivalent voltage source in series with a equivalent resistance. Well, here the voltage and current source could be a dependent or a independent sources, and it doesn't matter how complex the network is, you can apply this Thevenin's theorem. So if we apply Thevenin's theorem in this circuit, then we can replace entire circuit by equivalent voltage source in series with a equivalent resistance across this two terminal AB. So in general, if you have any linear bilateral network, then you can replace that network by a equivalent voltage source in series with a equivalent resistance across its two terminal. Well, if you don't know about linear and bilateral network, you can check my video on classification of electrical network. The link for the same is given in the description below. Now in the equivalent circuit, this voltage is known as a Thevenin's voltage and the equivalent resistance is known as a Thevenin's resistance. So Thevenin's voltage is the voltage that you find across the network after removing the load. Now similarly, the Thevenin's equivalent resistance is the resistance that you find across each two terminal after removing all the independent sources and replacing them by their equivalent resistance. So if you see any ideal voltage source, it has a zero series internal resistance. And similarly, if you see any ideal current source, it has a infinite parallel internal resistance. So to find the Thevenin's equivalent resistance, you can replace voltage source by a short circuit and current source by a open circuit. Now there are three different cases for this Thevenin's theorem. So let's see them one by one. So the first case is that the circuit contains all the independent sources. The second case is that the circuit contains independent as well as the dependent sources. And the third case is that the circuit contains only dependent sources. So we will see all the three cases with one example and we will see that how to find the Thevenin equivalent circuit for all the three cases. So let us see the first case where the circuit contains all the independent sources. So if you see the circuit contains the two independent voltage sources. And in this circuit, we need to find the Thevenin's equivalent circuit across these terminal A and B. So let us first of all find the Thevenin's equivalent voltage. So to find the Thevenin's equivalent voltage, first of all, let's remove this load. And now let's apply a Kirchhoff's voltage law in this circuit. So let us assume that the current I is flowing in this direction in this circuit. So if we apply a Kirchhoff's voltage law, then we can write 10 is equal to 10I plus 10I plus 20. That means 20I is equal to minus 10, or we can write I is equal to minus 0.5 ampere. So here the negative side indicates that the current is flowing in the opposite direction. Now here the Thevenin's voltage is nothing but the voltage across this terminal A and B. So the voltage VAB will be 10 minus 10 into I, that is 10 minus 10 into minus 0.5 ampere, which will come out to be a 5 volt. So in this way, the Thevenin's voltage across this two terminal is a 5 volt. So now let's find the Thevenin's equivalent resistance. So to find the Thevenin's equivalent resistance, we will turn off all the sources. So we will short circuit these two voltage sources. So if you short these two voltage sources, then the equivalent circuit will look like this. So the equivalent resistance across this two terminal AB is nothing but a 2 10 ohm resistors in parallel. So RTH will be nothing but a 10 ohm in parallel with a 10 ohm. So the value of RTH will be 5 ohm. So now if we draw the Thevenin's equivalent circuit, the circuit will have a Thevenin's voltage source in series with a equivalent Thevenin's resistance. And we have found that the Thevenin's voltage is a 5 volt and Thevenin's equivalent resistance is a 5 ohm. So now let's connect the resistor across this two terminal AB, which we have removed earlier before the calculation. And now suppose if you want to find a voltage or current across this two terminal AB, then you can find it easily. So in this way we can find the Thevenin's equivalent circuit for the case where the circuit contains all the independent sources. Now let us see the second case where the circuit contains independent as well as a dependent sources. So in this circuit we will first of all find the Thevenin's equivalent voltage across this two terminal AB. Now if you see this circuit contains two nodes. This is the first node A and this is the second node. Let us say that is a X. Now the Thevenin's voltage VTH is nothing but a voltage across this two terminal AB. So definitely the voltage at this node A will be nothing but a voltage VTH. Now if you see these two nodes, there is a voltage source between these two nodes. So we can consider this node as a super node. And we can treat these two nodes as a single entity. So now let's apply a KCL at this super node. So applying KCL, we can write Vx divided by 2 kilo ohm plus Vx minus 5 divided by 2 kilo ohm plus at this end you can write Vth divided by 1 kilo ohm is equal to 0, where Vx is the voltage at this node X. Now if you see at this super node, we can write Vx minus Vth is equal to 3 into VAB, and VAB is nothing but a voltage across this terminal A and B, and we can write VAB as a VTH. So Vx minus Vth will become 3 Vth, and hence Vx is equal to 4 Vth. So now we can put the value of this Vx in this equation. So putting this value, we will get 4 Vth divided by 2 kilo ohm plus 4 Vth minus 5 divided by 2 kilo ohm plus Vth divided by 1 kilo ohm is equal to 0. Or we can write it as a 8 Vth minus 5 plus 2 Vth is equal to 0. That means Vth is equal to 5 divided by 10, hence 0.5. That means Vth is equal to 0.5 volt. So in this way we found the Thevenin's voltage as a 0.5 volt. Now let us see how to find the Thevenin's resistance when the circuit contains a independent as well as a dependent sources. So in such cases, just short the terminal A and B where you want to find the equivalent resistance and find the short circuit current through this terminal A and B. So in this way you can find the Thevenin's equivalent resistance. So now in this case, if you see, if you just short the two terminal A and B, then this 1 kilo ohm resistor will also get shorted. Also, as this terminal A and B are short circuited, the voltage across these two terminal A and B is 0, and hence this dependent voltage source will also get short circuited. So if you see the equivalent circuit will look like this. And in this equivalent circuit, if you see, this 2 kilo ohm resistance also get short circuited. So if you see the equivalent circuit will have a 5 volt voltage source in series with a 2 kilo ohm resistor, and hence the short circuit current can be given as 5 volt divided by 2 kilo ohm, that is 2.5 milliampere. So the Thevenin's resistance can be given as Thevenin's voltage divided by this short circuit current, and we found the Thevenin's voltage as a 0.5 volt, and we got a value of this short circuit current as a 2.5 milliampere. So we will get a value of Thevenin's resistance as a 200 ohm. So if we draw the Thevenin's equivalent circuit, it will look like this. It will have a 0.5 volt voltage source in series with a 200 ohm resistor. So in this way we can find a equivalent Thevenin's resistance in a case where the circuit contains independent as well as a dependent sources. Now let us see the third case where the circuit contains only the dependent sources. So in such cases where the circuit contains only the dependent sources, the value of a equivalent Thevenin's voltage will be 0, as it doesn't contain any independent sources. Now in such cases, to find the Thevenin's equivalent resistance, just apply a test voltage or a test current across its two terminal. So either apply a test current or a test voltage across these two terminal, and using this we can find the Thevenin's equivalent resistance. So suppose if you are applying a test current, then just find the voltage across this test current, and the ratio of this voltage divided by the value of this current will give you the Thevenin's equivalent resistance. Similarly, suppose if you are applying a voltage as a test voltage across these two terminals, then the ratio of voltage divided by the current that is flowing through this test voltage will give you the Thevenin's equivalent resistance. So in this circuit, we will apply a test current of 1 ampere across these two terminals. So the first thing that you will see here is a I1 is equal to minus 1 ampere. So if you see here, the I1 is equal to minus 1 ampere. So now let us apply a KCL at this node A. Let us assume that the VA is the voltage that is appearing across this current source. So we can write VA divided by 4 plus VA minus 3I1 divided by 6 is equal to 1 ampere. Now already we have found that the I1 is equal to minus 1 ampere. So we can write it as a VA divided by 4 plus VA plus 3 divided by 6 is equal to 1. Or we can write it as a 3VA plus 2VA plus 6 is equal to 12. That means 5VA is equal to 6. Or we can write VA is equal to 6 by 5. So we will get VA as 1.2 volt. And hence the value of the Thevenin's resistance will be nothing but this value of VA divided by this test current, that is 1 ampere. So we will get value of the Thevenin's resistance as a 1.2 ohm. So in this way, if the circuit contains only a dependent sources, then by applying a test current or a test voltage, we can find the Thevenin's equivalent resistance. So before I end up this video, let us briefly see this Norton's theorem, as this theorem is dual of the Thevenin's theorem. So in the Thevenin's theorem, we had seen that any linear bielectrical network can be converted into the equivalent voltage source in series with a equivalent resistance. Now according to the Norton's theorem, you can replace any linear bilateral network by a equivalent current source in parallel with a equivalent resistance. So if you have any linear bilateral network, then you can replace it by a equivalent current source in parallel with a one equivalent resistance across its two terminal, where this current source is known as a Norton current and the equivalent resistance is known as a Norton equivalent resistance. So now Norton's theorem is exactly a dual of Thevenin's theorem. So if suppose someone tells you to find a Norton's equivalent circuit for all the previous example that we had seen, then just by using the source transformation, you can find a Norton's equivalent circuit. That means this current IN is nothing but VTH divided by RTH, and this Norton equivalent resistance is nothing but a Thevenin's equivalent resistance. So any circuit in which you have found the Thevenin's voltage and the Thevenin's resistance, using the source transformation you can transform it into the equivalent Norton circuit. If you don't know what is a source transformation, then you can check my video on a source transformation. So I hope in this video you understood what is Thevenin's theorem in the electrical circuit, and using this Thevenin's theorem how easily we can solve the circuit problems. So if you have any question or suggestion, please let me know in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.